Hello and good afternoon everybody. Thanks for joining us in this, which is the fifth of our product webinars for 2019. My name's Tom Pritchard and I'm the host for today's event. I'll be introducing the webinar and also rounding up at the end. In today's presentation we'll be talking about the advanced modelling features of LimitState Ring, and the discussions will give you a flavour of some of the less widely known about but possibly extremely useful applications of the software. This includes, amongst other things, how to diagnose the causes of existing cracks and also identify potential load paths under service loading. Total time for the webinar is about 45 minutes, and this should include 5 to 10 minutes at the end for any questions that you may have. You can post them throughout the webinar using the interface that you should have in front of you. We do try to answer as many of your questions as we can in the time available, but it's not always possible to do so, and we apologise in advance if we're unable to get round to yours. If we don't, then please feel free to contact us outside the webinar via info@limitstate.com, and we'll be more than happy to speak to you about it in detail. So, without further delay, I'd like to introduce our speaker for today, who is Matthew Gilbert, and he's the LimitState Ring Product Manager. I'll now pass you over to him.
Thanks, Tom, and thanks to everyone for joining us for the webinar today. Right, the first slide is just going to show you a couple of screen grabs from the LimitState Ring software, just to give you an indication of what we're all about. The first, the upper image shows a free-span bridge with railway loading, quite straightforward. The lower image gives an indication of some of the more advanced features that we can use using this software. So we have, instead of a single voussoir arch in the centre, we actually have a multi-ring brickwork arch, and we're actually using the facility to model partial ring separation to actually glue those different rings together close to the piers. And so actually all three spans actually got multi-ring brickwork arches. So we'll look at how we can actually achieve that in the software, amongst other things, during the webinar today. So what I'll do is, first of all, give you a very brief introduction to LimitState, the company that makes the software, then give you a background introduction to the topic, masonry arch bridge analysis in particular. Then the core of the webinar will be looking at 3 specific advanced modelling features. The first is using support movement mode, as we call it, to identify load paths under service loads and also the potential causes of cracks in an existing structure. We'll then look at how we can model specific defects in a bridge, and the final thing is we'll look at how you can include discrete reinforcement in a masonry arch bridge. Then wrap up with some conclusions, and then open the webinar to questions from yourselves. Okay, so first of all, just a few words about LimitState. We are here to provide engineers with software that primarily focuses on the ultimate limit state analysis and design state, effectively, so looking at the collapse state. To do that, we use methods that are not used by other mainstream software providers. We use optimization technology to do that. We endeavour to make sure the software is robust, well validated, and also easy to use and fully supported. I've just got a few company logos on the right there. We've got many hundred users now of LimitState software around the world. In terms of where we fit in compared with other tools that are available, on the one hand, at the sort of simple end of the spectrum, we can think of hand calculations or spreadsheets or very simple software applications that automate hand calculations. At the right hand side, you can imagine much more complicated tools, for example based on finite elements, discrete elements, and so forth. And where we position ourselves is right in the middle. We try to deliver the best of both. So we use numerical rigid plastic analysis techniques to rapidly and directly home in on the collapse load in most cases, although there's an exception that we'll cover today. And the idea is that you can set up and solve those problems very quickly, and also that you have a lot of the flexibility that you have with the advanced tools, in the sense that you can locally modify properties and quickly answer what-if scenario questions in a way that you can't often with simple hand calculation tools. So, background to the topic of today, masonry arch bridges. What do we know about masonry arch bridges? We know that there are many masonry arch bridges around and in service today. Here in the UK, where I'm speaking from, there are tens of thousands, and there are many tens of thousands worldwide in each country, or many countries you can consider of. So we reckon there's about 1 million spans in total in service around the world today. What they're typically doing is carrying heavy loads. Also, another feature is that there's a very diverse range of different geometries, so we have many unique details that we need to deal with as engineers. What's LimitState Ring? Well, it's an interactive software tool for investigating the stability of masonry arch bridges. That's the main purpose of it, although we'll also look at a different usage mode today. We can model single, multi-span arch bridges. We can model a wide range of different failure modes. We can model localized properties and defects, support movements, and the effects of reinforcement. Now, the main webinars will focus on the top two of those different areas of application. What we're going to focus on is the bottom three in that list, so localized properties and defects, support movements, and the effects of reinforcement in this particular webinar. Just very briefly outline how the software works. If we go right back to a very simple scenario, a single ring voussoir arch with a number of masonry units or voussoirs spanning between abutments, what we do is we discretize that arch into those voussoirs or rigid blocks. Of all the permissible equilibrium states, which we can visualize as the line of thrust that fits within the arch geometry, we basically use optimization to find the one corresponding to the maximum load factor, which also corresponds to the point at which you see collapse. And depending on the material properties, for example the friction coefficient, you may get a hinge mechanism, you may get a sliding failure like we can see now on screen, or you may get a combined failure mechanism. The optimization algorithm will find the most critical mode of response for whatever given set of parameters that you enter into the software. In terms of the mathematics, possibly slightly daunting, seeing lots of symbols on the screen, but really it's quite simple. What we're trying to do is, for a given axle loading intensity FL, we apply a factor, a multiplier lambda, and we try to maximize that lambda subject to some constraints. So it's an optimization problem, a constrained optimization problem. What are the constraints? The constraints are basically equilibrium and yield in plastic analysis parlance. So equilibrium, basically we look at each and every one of the blocks making up the masonry bridge. So for example, the grey block that's identified in the green ellipse, and we look at equilibrium in the horizontal direction, the vertical direction, and in the rotational sense, and we just make sure that that is validated everywhere, or satisfied everywhere. In terms of yield, then we've got quantities representing the forces between blocks, so the contact forces, so the shear, moment and normal force, S, M and N, and we can impose restrictions on those. So for example, the bottom one here, we've got minus mu times N is less than or equal to S is less than or equal to plus mu times N. That's basically saying that the shear force is limited by the normal force and the coefficient of friction. So in other words, at some point we'll end up with getting sliding failure. And similarly, the constraint above is actually for rocking. So we're linking the moment to the thickness of the interface and the normal force. So the nice thing about this formulation is it's linear, and so we can solve this very, very quickly on a modern desktop PC. So just to sort of pick out a couple of a few key points. So the main usage mode, we're focusing on collapse. We have a single limiting line of thrust or equilibrium state. We can easily find the load required to cause collapse using the method I've just described, and that's a normal usage mode in the software limit state ring. However, in service, when you're some distance away from the collapse state, which is obviously what you'd like to be in service, there are many possible lines of thrust or equilibrium states. However, if the supports move, we can identify a unique line of thrust, and that's basically what we take advantage of in the support movement mode in limit state ring, and we'll come to that shortly in the webinar. One thing I haven't mentioned that's important in a masonry bridge is the presence of backfill. So backfill surrounds a masonry arch element typically, or very commonly, and the way we model this in the software is quite simple. We don't model it directly, we model the anticipated effects. So the effects are to distribute the live load or disperse the live load, to provide vertical self-weight loading onto the arch, which effectively pre-stresses the arch and provides it with more resilience to movement. And finally, we model the effect of the passive effect of the soil as a piece of masonry arch barrel attempts to move into the surrounding soil. And we model that actually using what we call here backfill elements. So if you push parts of the arch barrel into the soil, those backfill elements are mobilized or activated. And if you move away from the backfill elements, then assuming that the active pressures are negligible, then you have no horizontal force applied. This comes up on the image that you can now see on screen. We've got a multi-span bridge, and you can see backfill elements that are mobilized in a couple of regions in this case. You can also see a thrust line, or strictly speaking a thrust zone, where the thickness of that line reflects the amount of material needed to support that thrust force. You also see hinges shown in red, and also the distributed load from the applied vehicle. So this is a typical scenario after you've solved a bridge problem using the software. Just say a couple of words about verification. Very important to us. The software was actually originally developed as a tool to interpret results from laboratory tests. So we had laboratory tests carried out in the early 1990s, and the results of these tests and also the correlation with the analysis was written up in a series of papers that appeared in the Structural Engineer in the 1990s, and both multi-span and single-span bridges were tested. More recently, we've carried out very small tests, for example at Sheffield, and also larger tests at Sheffield. These are the very small ones where we're able to try to decouple the different effects of the backfill. So, I mentioned passive restraint. If you actually bag up soil and place it on the arch barrel, then clearly there is no passive restraint. And so we're able to actually check that each of the elements that contributes to the load carrying capacity were being modelled reasonably accurately using limit state ring. And actually we found that that was the case for the tests that we carried out. So in every case, I think there were 7 scenarios. In every case it was within 10% of the limit state ring result. More recently, we've also been looking at larger scale tests in a sort of oversized fish tank in collaboration with the University of Salford, and using digital image techniques to try to understand how the soil moves around under the action of the loading applied to the structure. Okay, so then move on to the meat of the webinar today, advanced modelling features. The first one that I'm going to focus on is identifying load paths and the causes of cracks. And to do that, I'm going to use the limit state ring support movement mode. So support movement mode basically allows us to do two linked but separate things. One is to understand how the structure works under service loads, and secondly, it can help us diagnose the cause of cracks. So I'll just pull up the software. So I've got the software open now, and I'm just going to open up the bridge that you can see on screen, triple span bridge. So you saw on the previous slide. So here is the bridge. I'll say a few words about it. I actually described the geometry using the free-centered or pseudo-elliptic built-in geometry. There's a range of built-in geometries: segmental, free-centered, pointed. What I would, however, say is it's generally much better to use one of the user-defined shapes, so multi-segment or interpolated, using data taken from the field, so you've actually got a good representation of your field bridge in your model. And that's because it's the shape of the arch, barrel and other masonry elements in relation to the applied load that governs stability. So if you get that shape wrong, then all your outcomes from your analyses are likely to be inaccurate, effectively, or not particularly accurate, depending on how far away you are from the true shape. Here, however, just for simplicity, I'm using the free-centered shape. I've also got a vehicle on the bridge. I can move that vehicle around and see how this affects the mode of response. I've also got something in the output pane, which is an additive factor, and that is a multiplier on the applied load at the point of collapse. So what I could do is just move this around to find manually what the minimum value is. It's about 3.5 by the looks of it. Or there's a function in the software where I can actually just traverse the vehicle right across the bridge, and it will tell me what the minimum adequacy factor is. In this particular case, if I go to the loads dialog, I can see that I've actually got a 40-ton 5-axle vehicle, which has got a series of axle loads as shown in this dialog here. I can define any vehicles I want manually, or I can use some of the built-in vehicles in the library. I can also make changes. So if I select, using the select tool, for example, a series of contacts, then I can, for example, change the masonry strength, or I can, for example, glue the elements together to represent, for example, the presence of a large, effectively rigid block above the pier, which is sometimes what you see. But here, what I want to do is actually move on to using support movement mode. I'm not currently in support movement mode, I'm in a normal mode, so when I click the green button or when I drag the vehicle, then automatically it calculates this additive factor. Now what happens if I take this vehicle away? Software becomes a little bit confused. It can't find an additive factor because that's the multiplier on the applied load required to cause collapse, and when the load is off the bridge, then it can multiply that vehicle load forever and a day and it won't cause collapse. So what I'm going to do is actually switch to support movement mode, so tools, support movement wizard, and what I'm going to do is, initially just for simplicity, I'm just going to spread each of these spans, say by a small distance. So if I select that skew back there, and let's say that skew back moves by 1 millimeter in the right to left direction, I then select another support. I don't need to move the first pier support, I can move the second one. If I move that one by 1 millimeter, so I'm basically going to have the first two spans are going to be spreading by 1 millimeter, and then if I also choose the right hand support, then I can assume that say moves by another millimeter, so 2 millimeters in total. So if I click OK and then I click solve, then even though I don't have a vehicle on the bridge, I should get a result. And the result I get is effectively the situation when each of these supports or each of these spans spreads outwards slightly. You can see it's a nice simple free hinge arch. You also see in this particular case that I've actually got fill above the piers, but I've also got these darker elements indicate that I've got some backing in there as well. Now what I can do is I can bring this vehicle back into the equation. I can bring this back onto the bridge, and what you can see is that by doing so I'm actually influencing the locations of the hinges in the structure. So what's actually happening is we've got potentially opening and closing of masonry joints under the action of this vehicle. And if you find that under the action of a vehicle that's going to be commonly crossing your bridge, you have significant opening and closing, then potentially the long-term lifespan of that bridge could be brought into question. In this particular case, the hinges are moving, but they're not moving, well, actually are moving a fair amount, but we don't have, for example, reversal of the direction of the hinges. So in other words, we don't have an area which is in compression when the vehicle is in one part and in tension when it's in the next part. It's not visibly so, at least. But it's a useful tool to try to get to grips with what your bridge is typically experiencing under the action of regular loads, or under the action of, for example, special loads that might be required to cross your bridge. In terms of the output window, we now move on to a different output. We don't have an additive factor, we have something called work. And to explain that, I'll go back to the slides. How does the software work in this mode? Well, actually we changed the objective function. We're no longer maximising the load factor, we're minimising the work done by the supports, or the energy. And the rest of the formulation is very, very little changed from before. So we end up with a very, very similar set of equations to solve compared with normal mode. In terms of the usefulness of the output, clearly this is not directly useful to note the energy, although you can use it to infer, for example, what the support reaction is. So this is the case I've just looked at, and actually, what I'm going to do is actually refer to a bridge of a very similar geometry. I actually set this model up to approximately represent a bridge near Leeds, Linton Bridge, which was actually affected by the 2015 Boxing Day floods. I go back to the model. In this model, I was busily looking at spreading of supports. What I'm going to do is just clear those existing support movements and instead look at what happens if one of these piers settles quite significantly. So in the case of Linton Bridge, one of the two piers settled quite markedly by the order of a couple of 100 millimeters, and I can model that if I just enter minus, because positive is upwards, so minus is downwards, and put in 200, and then solve that problem again, and you can see that you have a representation of what happens to this bridge when you have a support movement of that nature. If I want to look at it in a bit more sort of detail, I can kind of also try to imagine what this looks like from the underside of the bridge. You can see we've got a transverse crack relatively close to the pier in the first span, and also cracking in the middle span as well. If we go back to the slides, we can zoom in on this first span, and actually we can see that we do have that transverse crack that we expect to see. In this particular case, it's probably a little bit further up the arch from the pier, but that's largely down to my assumptions on the level of backing in the bridge, and if I adjust those, then potentially I could get better correlation. So actually, when a bridge suffers a support movement, actually it's a very, very good opportunity to refine your model, because effectively it's a free test that you can use to help build a better model. Now, if the bridge is so badly damaged it needs to be replaced, then that's not much use. But if unless the bridge is representative of many other bridges, for example on a stretch of railway line, in which case it could still be useful. If the bridge is going to be repaired, then this helps you ensure that the bridge model next time is more accurate. And this shows another image of Linton Bridge. This is the view from the roadway, and you can see very clearly the large settlement causing the parapet line to distort markedly. Got another example shown on screen now. This is actually a railway bridge. This particular bridge had a support movement that happened a long time ago, I think around the time of the First World War, relatively soon after it was constructed. It's mining subsidence, and the bridge is carrying live trains, so recent interest in trying to understand exactly what the consequences of this quite severe distortion were in terms of the murder response of the structure. So you can see the parapet line distorted, and also the spans also quite badly distorted. So what we did in this case was was look at the bridge in the field where the cracks were, to try to actually infer what the likely support movements were in reality. And actually, with this particular set of support movements, we've got pretty good correlation between the observed and modelled crack patterns. And the other interesting thing in this bridge was actually modelling looking at the capacity of the bridge with quite severe distortion, particularly of the right-hand span. And in this particular case, found that the consequences of the distortion on capacity was actually not that great. So I think something that you have to look at on a case-by-case basis. Sometimes quite severe distortion can be less damaging than you might think. So the second thing is looking at specific defects in a bridge. So what you can do is zoom in on any given block, contact, or series of blocks and contacts, and actually specify local parameters in the property editor. Got a little sort of benchmark example. This is a series of small arch ribs that we tested in the lab some years ago. In the case of arches 3 and 4, we had partial ring separation. We go back to the software and open the model. So this is for the arch 1, where we had no ring separation, and we get a simple mechanism. And in this particular case, we got get an address factor of about 4, which is actually very close to the scenario that we found in the lab. I can, using the software, very easily model this as multi-ring. So instead of being a single ring of bricks, I can have 2. So in this case, 107.5 each. If I solve, then we get different mode of response, distributed hinges, and a much lower adduccy factor. But if I want to model the partial ring separation, or more particularly the fact that in this particular bridge we had a number of either plates or headers, so that's through thickness units, then we can actually model that. We can glue the bricks together to model that scenario. I just need to work out where exactly it's going to be. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think it's there. And the same here. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's there. So if I can now model those as not permitting either sliding or hinging, and then do an analysis, and we end up with a different scenario again. The adduccy factor that started off being about 4 went down to 1.47 when we had the ring separation, is now back up to 3.2 roughly. So you can see how you can easily enter those sort of properties. And this is what we found experimentally, and we found very similar results to the ones that we can see we've just seen in the model. And this is a table that just shows you the correlation. Quickly look at a field example. This is actually a small brickwork culvert, partial ring separation. So there was basically ring separation through most of the span, but there was good bonding between the different rings near the abutments. And this shows the outcome. So we're able to model both the behaviour and also model the impact on load carrying capacity. So this particular case, we had quite significant reduction in load carrying capacity. So that gives you an indication that if you are able to reliably stitch these rings back together, then you can restore some of the original capacity. Okay, so lastly, move on to the third of the advanced areas that we wanted to cover in this webinar, modelling reinforcement. What we can do in the software is we can add reinforcement elements either on the surface or at a given depth. So what we basically assume is that we have a rectangular crush block for the masonry, and then we have a tensile or compressive force applied to represent at the location of the reinforcement. Very, very small change to the formulation that you saw earlier. The things that you do need to bear in mind, however, are that we're assuming rigid plastic behavior, so we're assuming that the reinforcement yields in a ductile manner at the prescribed force, and that we assume that we're not going to get brittle behavior. So in other words, the ductile behavior that we expect before the reinforcement, we're going to get after the reinforcement has been applied to the structure. So you do need to be careful when you're using this functionality. Validation, we have, for example, looked at the results from some tests carried out by the Transport Research Laboratory some years ago. They had a couple of bridges, one with reinforcement, one without. In this particular case, the bridge reinforcement had basically embedded reinforcement, 90 millimeters from the intrados. The tensile force of the reinforcement was around 149 kilonewtons, and I'll very quickly just show you how you can do that in the software. So if we open up the relevant structure, click solve. This is the unreinforced structure. We have an adequacy factor of 198. You see it's 3 separate rings behaving to some extent independently. If I want to add reinforcement, then I go to the edit bridge dialog and say that we have reinforcement. I then can select all the rings in the first ring, all the blocks in the first ring using the select contacts tool, and then I can enter the details that you saw on the previous slide. So for example, that we've got reinforcement at 90 millimeters depth. We've got reinforcement that gives us 149.3 kilonewtons force in certainly in tension, but probably in compression as well. And if we enter that, you can see now we've got the reinforcement there. If we click solve, then we end up having an increased load. Capacity goes up from approximately 200 up to 325. And I can show the thrust line. The thrust line doesn't really make a lot of sense now because we've got thrust lines that lie outside the thickness of the masonry. So instead, we can look at moments, shear forces, which are large, generally more useful for this kind of scenario where we no longer have pure arching action. Okay, so I think that's coming to the end of the webinar. Just wrap up with a few conclusions. So, support movement mode that we looked at to start with. 2 things it allows us to do basically. It allows us to look at potential load paths under working loads, and it also allows us to look at the likely causes of existing cracks, and that can be very useful, for example, in deciding whether it's worth investing in underpinning. Sometimes the behavior can be a little bit counterintuitive, and it's useful to have a tool like this to explore various different options. Second thing that we looked at was dealing with local defects, so for example, partial ring separation, but we could have looked at a variety of different local defects, so for example, local mortar loss, or the effects of patch repairs where we've perhaps got different unit weight masonry and so forth. And lastly, we looked at reinforcement. Bear in mind that you assume that full strength can be mobilised and a ductile failure, so it needs to be used with care, but if you use it carefully it can be very useful in giving you an indication of the likely benefit of any given reinforcement programme. Okay, so that brings me to the end of the presentation. I've just got a short time for questions. So just have a look at the comments that we've got. Just got a question here. Can you specify how the live loading is distributed through the backfill? Okay, so I didn't cover that in this particular webinar. If we go to the materials dialog and we go to the backfill dialog, then you can enter the relevant details here. So you can enter the fact that you're modelling dispersion of the live load, and if you click advanced, then you can actually specify how that load is dispersed. Is it following a truncated booster-esque pattern, or is it a uniform pattern, and also what the cut-off angle is. So yes, you can specify how it's distributed. You can also specify actually how it's distributed through the surface fill as well. So there is actually an angle of dispersion there. And in the transverse direction, you can specify for the benefit of using automatic effective bridge width calculations, you can also specify transverse distribution angles as well. And you can see then, if we zoom round, we can actually then see, in that case, how the effective width varies depending on where the load is applied. Okay, I'll just see if there's any other questions. It doesn't look like we've got any burning questions at this point, so what I'll do then is I'll just pass back to Tom, who will wind up the webinar.
Thanks, Matthew, and thanks to all of you for attending today. We've now reached the final part of the webinar. Obviously, we hope that you learned something new about the software that maybe you didn't already know could be done. And obviously, if we have prompted any questions, then please do get in touch, like we said at the beginning, via telephone or via info@limitState.com, and we'll be more than happy to help you out. For people who aren't current users of LimitState Ring, we might try and get in touch with you over the next few days to find out if you do have any further questions, and to see whether you think LimitState Ring will be a useful tool for you. If you'd like to watch the webinar again, or certainly if you think you might know somebody who would be interested to see it, then we'll make a recording available very soon, possibly later today or early tomorrow, on our YouTube channel, and we'll email you with a link once it's available. We also have a collection of other previous webinars available to view on that YouTube channel, including introductions to LimitState Ring. So please just visit youtube.com/LimitStateSoftware and you'll be able to see what's available there. Finally, please look out for further event notifications that we'll be sending out, posted on our website and also on our social media, that will be telling you about future webinars that will be dealing with both LimitState Ring and our other pieces of software. So lastly, I'd just like to say thank you all for listening and hope you can join us again in the near future. Goodbye.